In the previous few lectures, we have seen some of the spatial orthogonal curvilinear coordinate systems, and those were actually the Cartesian coordinate system and cylindrical coordinate system. In fact, in those coordinate systems, you have seen how the scale factors h1, h2, and h3 can be found in a particular coordinate system. And after getting the values of those scale factors, we have seen how we can find the expression for the arc length, for the volume element, and also some of the important mathematical operations like gradient of a scalar function, divergence and curl of a vector function. And apart from that, we have also seen the expression for a very important mathematical operator which is known as Laplacian operator in those coordinate system. Now today we are going to discuss these things in another specific orthogonal coordinate system, and this is actually the spherical polar coordinate system. In fact, this spherical polar coordinate system is very important for the study of physics because you will find its application at several places while studying the different branches of physics. And you have encountered this spherical polar coordinate system while you study of physics. So today we will see how the scale factors we can calculate in this spherical polar coordinate system, and after getting the value of scale factors in spherical polar coordinate system, how we can find the expression for all those things which we have actually studied in the previous lectures. And for that, let us see this figure which I have drawn here. You can see I have shown three coordinate axes OX, OY and OZ of the Cartesian coordinate system, and there is a point P in a space whose position vector OP is equal to R in Cartesian coordinate system. And let us consider that X, Y and Z are the space coordinates or the position coordinates of the point P. Now, to find the value of this X, Y and Z coordinates, what you do? I hope you have an idea for this. We draw a perpendicular PR. You can see this figure. This PR is a perpendicular drawn on the XOY plane. And when you will join this point O, that is origin, to the foot of the perpendicular, that is the point R, then this OR is actually the projection of OP, that is R, or the position vector of point P in XY plane. So OR is what? This is actually the projection of R in XY plane. Now, to get the value of X and Y coordinates, we draw perpendicular on X-axis and Y-axis from the point R. And for that, you should draw a line RQ just parallel to the Y-axis. And you know, if the line RQ is parallel to Y-axis, it will be perpendicular to X-axis. So this angle at Q is pi by 2, that is 90 degree. And so this projection OQ is actually the X coordinate. So I have marked here that OQ is equal to X. And similarly, when you will draw a line RM parallel to the X-axis, this will be perpendicular to Y-axis, and so the angle made by this line at M is pi by 2. And so this projection OM, this is equal to Y, as you know. Again, if you will draw a line PN, see the figure. If you will draw a line PN parallel to this projection OR, which lies in XY plane, then this PN is perpendicular to Z-axis. So the angle at N is equal to pi by 2, and this projection ON will be equal to Z. So you can say that OQ is equal to X, OM, which is also equal to QR, this is equal to Y, and ON, this ON is equal to Z. So these are the X, Y and Z coordinates of the point P. Now let us consider this angle at O, that is angle NOP. This is equal to theta, and the angle ROQ, this is phi. So actually this R, theta and phi are known as the spherical polar coordinates of the point P. Now in this case, as you know, in any orthogonal curvilinear coordinate system there are two coordinate surfaces. So here we will define the not two but three coordinate surfaces. So here we will define the three coordinate surfaces, and as you can see, these coordinate surfaces are defined by the equations r equal to constant. Actually r equal to constant represents the system of concentric spheres. The another coordinate surface is represented by the equation theta equal to constant, and actually it gives a system of cones having the vertex at the origin and axis along the z-axis. You can say this cone will be like this. This has a vertex at O, and z-axis is its axis. And similarly, the third coordinate surface is represented by the equation phi equal to constant. And actually this gives a family of planes intersecting along the z-axis. So these are the coordinate surfaces. Now to find the value of scale factors, first of all we will see the transformation equations. That is the transformation equation between x, y, z and r, theta, phi. Here you can see r, theta and phi are the spherical polar coordinate system. So you can say that r is just equal to u1, theta is equal to u2 and phi is equal to u3. Now for getting the transformation equations between x, y, z and r, theta, phi, let us see this figure. In fact, you can see this OQR is a right angle triangle, and the angle at Q is 90 degree, and similarly OPN is also a right angle triangle, and the angle at N is also 90 degree. So I have drawn here those right angle triangles for your convenience in the actual form. You can see this is your right angle triangle OQR, and you have seen that this projection OQ is equal to x, QR is equal to y, and this in this second figure this ON is equal to z. You have seen just now in the first figure. Now you can see from this geometry of the figure that cos phi will be equal to what? This will be x divided by OR, and so x will be equal to OR cos phi, OR cos phi. And again you can see this figure that is ONP, triangle ONP, which is a right angle triangle, and from this figure you can see that sin theta will be what? This will be actually equal to Pn divided by r. So Pn will be equal to r sin theta. But as you can see the first figure, that this Pn is equal to OR. Pn is equal to OR, you can see. And so this Pn, which is equal to r sin theta, that is also equal to OR. So let us substitute this value of OR here. So when we will substitute the value of OR, which is r sin theta, we get x equal to r sin theta cos phi. This is the first transformation equation. You can see if we know the spherical polar coordinates r, theta, phi of a point, we can easily find what will be the Cartesian coordinate x of that very point. So this is the first transformation equation. Again, you can see from the first figure here that sine phi will be equal to y divided by OR. You can see y divided by OR, this will be equal to sine phi. So y is OR sine phi, and as you have seen that this OR is equal to Pn, so OR has been replaced here by Pn. But we have already evaluated here Pn. You can see this is r sine theta. So Pn is equal to r sine theta. So y is r sine theta sine phi. And this is your second transformation equation. Now from this figure, you can see here from the right angle triangle ONP, cos theta will be what? You can see this will be simply ON divided by OP, that is Z by R, and so Z is R cos theta. So this is your third transformation equation. So you can see there are three transformation equations: x equal to r sine theta cos phi, y equal to r sine theta sine phi, and z equal to r cos theta. For your convenience, I have actually proved these transformation equations, but for the further study or for the use of these transformation equations in several chapters of physics, you must remember it. So I will suggest you that you have learned how these transformation equations can be obtained, but for your convenience, you must remember these three transformation equations. So you can see I have mentioned here all these three transformation equations directly. Now we are going to find the expression for arc length in a spherical polar coordinate system. As you know, or you can see that this x is a function of r, theta and phi. Similarly, y is also a function of r, theta and phi. But z is a function of only r and theta. It means z is independent of phi. So in general, you can say that x is equal to a function of r, theta and phi. So if you want to calculate the value of dx, then you must follow the rules of partial differentiation, because x is not a function of only one variable, but it is a function of three independent variables r, theta and phi. So what will be dx? You can see this will be del x by del r dr plus del x by del theta d theta plus del x by del phi d phi. Now see these results. Not results, but only this result, that is first x equal to r sine theta cos phi. So as x is equal to r sine theta cos phi, you can easily find the derivatives del x by del r, del x by del theta and del x by del phi. You can see what will be this del x by del r. Del r by del r will be 1 and sine theta cos phi will be treated as constant. So del x by del r dr, this will be sine theta cos phi dr. Again, del x by del theta, you can see here sine theta will be differentiated, r and cos phi will be treated constant, and dc of sine theta will be cos theta. So this will be r cos theta cos phi d theta. And the third term is del x by del phi d phi. Now see what will be del x by del phi. When you will find del x by del phi, you will differentiate cos phi and r sine theta will be treated as constant. And dc of cos phi will be minus sine phi. So here will be minus r sine theta sine phi d phi. And similarly, you can see that as y is also a function of r, theta and phi, so dy will be written as del y by del r dr plus del y by del theta d theta plus del y by del phi d phi. And again we will find the derivatives del y by del r, del y by del theta, and del y by del phi from this transformation equation. That is y equal to r sine theta sine phi. And you can easily find it. When you will find del y by del r, that will be simply sine theta sine phi, because del r by del r will be 1. So you can see I am not repeating all the terms. You can do this simple differentiation easily. So after getting the value of those partial derivatives, you will get the value of dy like this. Dy equal to sine theta sine phi dr plus r cos theta sine theta d theta plus r sine theta cos phi d phi. Again you can see, since z is only a function of r and theta, not of phi, so dz will be del z by del r dr plus del z by del theta d theta. And we have seen that this z is equal to r cos theta. So what will be this del z by del r? You can see this will be simply cos theta, because del r by del r 1. So this is cos theta and dr is here. So repeat the term dr. And del z by del theta will be what? In this condition, we will treat r as constant, and dc of cos theta will be minus sine theta. So this will be minus r sine theta d theta. So in this way, you can see that we have obtained the value of dx, dy and dz. Now, as you know, in Cartesian coordinate system, the square of the arc length, which we denote by the symbol ds square, is simply equal to dx square plus dy square plus dz square. Now, as we have obtained the value of dx, dy and dz just now, so when you will put the value of dx, dy and dz in this equation, you will get the value of ds square. Actually, here there will be a lot of algebra, but that algebra you can do. You have only simply to put the value of dx, dy and dz, and after squaring those terms and doing in the algebra, you will get this result. Actually, I have not done those algebra. This is just a homework for you. You can try yourself, and definitely when you will try yourself after the substituting of value of dx, dy and dz in this equation, you will easily see that ds square will be equal to dr square plus r square d theta square plus r square sine square theta d phi square. I am again saying you that I have not done those algebra, but you should try yourself and then you will get this result. But as we can see that we have treated that r is equal to u1 here, theta is equal to u2 and phi is equal to u3 in terms of the symbols of general orthogonal curvilinear coordinate system. So this dr, d theta and d phi can be replaced by du1, du2 and du3. So when we will replace this dr, d theta and d phi in terms of du1, du2 and du3, our result will be what? This will be ds square equal to du1 square plus r square du2 square plus r square sine square theta du3 square. But as we know, in general orthogonal curvilinear coordinate system, the expression for ds square is this much. You have seen this expression earlier. This is h1 square du1 square plus h2 square du2 square plus h3 square du3 square. So you can equate these two equations 1 and 2 because both are equal to ds square. So let us equate these two equations. You can see I have equated these two equations. Now as you know that these u1, u2 and u3 are independent variables. So du1, du2 and du3 will be also independent from one another. And if du1, du2, du3 will be independent from one another, then this identity will hold only when the coefficients of du1 square, du2 square and du3 square in both LHS and RHS will be same. So definitely we must equate the coefficients of du1 square, du2 square and du3 square in LHS and RHS. So you can see the coefficient of du1 square in LHS is what? This is h1 square. But the coefficient of du1 square in RHS is 1. So you can write h1 square equal to 1. And if h1 square is 1, you can simply say that h1 is equal to 1. So the first scale factor is equal to 1. You can see in the spherical polar coordinates. Now equate the coefficient of du2 square. You can see in LHS the coefficient of du2 square is h2 square, and that in RHS it is r square. So h2 square will be equal to r square. It means h2 is equal to r. This is your second scale factor in spherical polar coordinates. Now equate the coefficient of du3 square in LHS and RHS. You can see in LHS it is h3 square, but in RHS this is r square sine square theta. So h3 square is equal to r square sine square theta. It means h3 is equal to r sine theta. So in this way you can see we have obtained the scale factors particularly in spherical polar coordinates. And what are those? Those are 1, r and r sine theta. It means h1 is 1, h2 is r and h3 is r sine theta. Now once we know the values of these scale factors, now it will be very easy to calculate all those things which we have discussed in the previous lectures. So you can see, first of all, I am going to find the expression for the volume element in a spherical polar coordinate system. And for these calculations, you must remember the results of the previous lectures. For your convenience, I have mentioned always the results of the previous lecture, and then we will apply the result for the in case of a spherical polar coordinate system. So see here, the general expression for the volume element dV in orthogonal curvilinear coordinate system, you know, you have seen this result in earlier lectures. This is equal to h1, h2, h3, du1, du2, du3. But as you can see, h1 is 1, h2 is r and h3 is r sine theta. And here u1, u2, u3 are r, theta and phi. So what will be this? This will be 1 into r sine theta into dr, d theta, d phi. So dV is r square sine theta dr, d theta, d phi. Actually, this expression of volume element in a spherical polar coordinates is very important. We have derived this result here, but I will suggest you for its use in several places in study of physics, you must remember it. You have to remember it because you cannot derive always it. So you must remember this expression for the volume element for its use in several places in physics. So see this expression and try to remember it. Now, after getting the expression for the volume element and the arc length, now we will discuss the expression for the important vector operations of vector analysis and also the expression for the Laplacian in a spherical polar coordinate system. So let us see first of all the expression for gradient of a scalar function. Let us consider that psi is a scalar function. Then you know grad psi. Grad psi means gradient of psi. This is symbolically written as del psi. And how this del psi or grad psi is defined in general orthogonal curvilinear coordinate system? I have repeated this expression because you have already seen the proof of this expression in the earlier lectures. But for your convenience, I have mentioned it again here. In general, we know this del psi is equal to 1 over h1 del psi by del u1 e1 hat plus 1 over h2 del psi by del u2 e2 hat plus 1 over h3 del psi by del u3 e3 hat. Actually, you have seen that this h1 is equal to 1. So here this will be 1 over 1, that is 1. And u1, u2, u3 in this case are what? They are actually r, theta and phi. So u1 will be replaced by r, u2 by theta and u3 by phi. Similarly, here we consider the three orthogonal unit vectors er, e theta and e phi instead of e1. It means instead of e1, now we will write er hat. Actually, this is a unit vector in the increasing direction of r. And instead of e theta, in this coordinate system, we will write instead of e2 hat, we will write e theta hat. Actually, this e theta hat is a unit vector in the increasing direction of theta. And instead of e3 hat, we will write e phi hat. So, after substituting the value of scale factors h1, h2 and h3 and replacing u1, u2, u3 by r, theta, phi, you will get the expression for gradient of the scalar function psi like this. This is del psi by del r er hat plus 1 over r del psi by del theta e theta hat. And since h3 is r sin theta, so the last term will be 1 over r sin theta del psi by del phi e phi hat. So this is actually the expression for the gradient of a scalar function in a spherical polar coordinate system. Now we will see the expression for divergence of a vector function. Let us consider that this f is a vector function, and in a spherical polar coordinate system we will denote it by fr er hat plus f theta e theta hat plus f phi e phi hat. But to know the expression for divergence of f, that is del dot f, I have again mentioned the general expression which we have obtained earlier. So you know, in the general orthogonal curvilinear coordinate system, divergence of a vector field f is defined like this. This is 1 over h1, h2, h3 times del del u1, f1, h2, h3 plus del del u2, f2, h1, h3 plus del del u3, f3, h1, h2. We have seen earlier. Now what you will do? Now it is very easy to find this divergence of vector function f in a spherical polar coordinate system. For that, what you will do? We will simply substitute the values of all these scale factors which we have obtained just now in a spherical polar coordinate system. And again, we will replace u1, u2, u3 by r theta phi, and f1, f2, f3 will be replaced by fr, f theta and f phi. So you can see what will be this. This will be 1 over h1 is 1, h2 is r and h3 is r sin theta. So this is 1 into r sin theta. And del del u1 will be written as del del r. f1 has been written as fr, and h2, you know, this is r, and h3 is r sin theta. In second term, u2 is now written theta, so this is del del theta, and f2 will be written f theta, h1 is 1 and h3 is r sin theta. And in the last term, u3 means now phi, so this is del del phi, f3 will be written f phi, h1 is 1 and h2 is r. Now you can see as in first term, we will differentiate the function partially with respect to r. So this sine theta will be treated as constant. So this sine theta will be taken outside of the differential operator, and inside the differential operator there will be only fr into r square, and sine theta will be outside. In second term, you can see, since we have to differentiate this in this second term partially with respect to theta, so this r will be treated as constant. So r will be taken outside of the differential operator. And in last term, differentiation is partially with respect to phi. So here this r will be treated as constant. So taking these things under account, you can see I have written it in the simplified form here. Here sine theta is outside of the differential operator, and here r is outside of the differential operator, and here also r is outside of the differential operator. Now, when you will multiply by 1 over r square sine theta to all the three terms inside this square bracket, what will be your result? You can see in first term this sine theta and sine theta will cancel out, and so our result is 1 over r square del r square fr. In second term, one of the r will cancel out, so this will be 1 over r sine theta del theta sine theta f theta. And in the last term, again one of the r will cancel out, so this will be 1 over r sine theta del f phi by del phi. So this is your expression for the divergence of a vector function f in a spherical polar coordinate system. Actually, these results are very important and its importance you will find when you will study particularly the spherically symmetric system in the study of electrostatics, electrodynamics, quantum mechanics, and at several places, also in nuclear physics. So this is very important result. I have derived this result here, but again I will suggest that you must remember these results for its use in different places of physics. Now we will see the expression for the another very important operation, that is called curl operation in vector analysis. And you know the general definition of curl of a vector function f in a orthogonal curvilinear coordinate system is like this. We express it in the determinant form like this: 1 over h1, h2, h3, and under the determinant you can see here there is h1 e1 hat, h2 e2 hat, h3 e3 hat, del u1, del u2, del u3, and in the third row we write h1 f1, h2 f2, and h3 f3. We have seen this expression for curl of a vector field f in your previous lecture. Now if you want to find the expression for curl of a vector field f in particularly the spherical polar coordinate system, what you will do? You can easily now say we will simply substitute the values of h1, h2, and h3 which we have obtained. Can you say what is the value of h1? I hope you have now definitely the values of h1, h2, h3 in your mind. h1 is equal to 1, h2 is r, and h3 is what? This is r sine theta. Again, these unit vectors e1 hat, e2 hat, e3 hat will be written as er hat, e theta hat, and e phi hat. And u1, u2, u3, these will be replaced by r theta and phi. And again, the components of the vector field f, which are f1, f2, and f3, now for convenience we will write it fr, f theta, and f phi. And again in the third row we will substitute the values of h1, h2, h3. So after Using the appropriate value of h1, h2, h3 which we have obtained in orthogonal spherical polar coordinate system, the expression for curl of f you can see it will be this like this. This is in fact 1 over 1 times r into r sine theta, and this product will be simply equal to in fact r square sine theta, you can see, and h1 er, but h1 is 1, h2 e theta, h2 is r, h3 e phi, h3 is r sine theta, and u1, u2, u3 has been replaced by r theta phi, and here we again put the value of h1, h2, h3. So this is the defining equation for the curl of a vector field f in a spherical polar coordinate system. I hope you have an idea, you have a knowledge to simplify this determinant. So I have not simplified this determinant, and it is easier to remember the expression for curl of f in this determinant form. So you must remember this expression in determinant form, and whenever it will be needed to simplify it, you know it, how this determinant will be evaluated. Now finally, we are going to find the expression for the very important mathematical operator which is called Laplacian or Laplacian operator. For this, I have again mentioned the general expression of this Laplacian del square in orthogonal curvilinear coordinate system. You can see the expression. Actually, you have seen this formula in the previous lectures, but for convenience, I have repeated it here. In fact, this del square in orthogonal curvilinear coordinate system, you have seen this is 1 over h1, h2, h3 times del u1 h2 h3 by h1 del u1 plus del u2 h1 h3 by h2 del u2 and plus del u3 h1 h2 by h3 del u3. Now you can think what we have to do here. If you want to find the expression for this Laplacian in a spherical polar coordinate system, again we will do the same thing. Put the values of h1, h2, h3, and you know h1 is 1, h2 is r, h3 is r sine theta. So this product of h1, h2, h3 will be r square sine theta, and u1 will be now written as r, and h2 by h3 over h1. h2 is r, h3 is r sine theta, so this will be r square sine theta, and h1 is 1. So I have not written here 1 because by division by 1 makes no change, so I have not written here 1. And del u1 is now del r. Now del u2, so this will be del theta, and h1, h3. h1 is 1 and h3 is r sine theta are divided by h2. h2 is r. So this r and this r will now cancel out, you can see here, and del theta. And the third term will be del phi, and h1 h2 by h3. You can see h1 is 1 and h2 is r. So here in numerator there is r, and divided by h3 which is r sine theta. So r and r will again cancel out. Now see, in first term we are going to find the partial derivative with respect to r. So this sine theta will be treated as constant. So in first term sine theta will be outside of the differential operator. In second term, since we have to do the partial differentiation with respect to theta, so here r will be treated as constant, but there is no term inside the term like r here inside the bracket. So here nothing will be outside of the differential operator. And in the last term, differentiation is partial with respect to phi, so this sine theta will be treated as constant, and this will be outside of the differential operator. So taking these things under account, what will be the expression? You can see here sine theta has been taken out outside of the differential operator, and in last term this 1 over sine theta have been taken out outside of the differential operator. And so when you will multiply by this r square 1 over r square sine theta to the terms inside the square bracket, you can see in first term sine theta will cancel out, so this will be 1 over r square del r square del r, and in second term this will be 1 over r square sine theta this much, and in last term sine theta times sine theta will become sine square theta, so this will be 1 over r square sine square theta del 2 by del phi square. So this is the expression for the Laplacian in spherical polar coordinates. If you have studied the problems in electrostatics, boundary value problem, the solution of Laplace equation in a spherical polar coordinate system, definitely you have used this expression for Laplacian. Similarly, in quantum mechanics, when you study the hydrogen atom or the rigid rotator, or you can say a problem in fact in central potential, then we need the expression for Laplacian in a spherical polar coordinate system. But these are some of the important examples. It does not mean that this Laplacian is used only at those places, but it finds its application at several places when we study the physics. So this is all about the spherical polar coordinate system, particularly when you study the orthogonal coordinate system. So these are the facts which we must remember. Although I have mentioned all these things with proof, but again finally I suggest you must remember all these results for the convenient study of your physics.